Okay, let's tackle example 2. Heat flow through a round slab. Here, we've got a pan of grilled potato rounds that's kept on an electric warming tray. So let's draw the situation. These potato rounds are discs, circular discs, and they have a height of 0.005 meters. We'll convert straight to meters because it's going to be useful. And the diameter is 5 centimeters, or 0.05 meters. The bottom surface is isothermal at 70 degrees centigrade, and the top surface is at 60 degrees centigrade. So we know heat transfers from high temperatures to low, so heat is transferring in that direction. So we'll set our coordinate axis in that direction too. It doesn't matter which way we set our coordinate axis, we will get the correct sign answer. Okay, so the question here is, given a thermal conductivity for potatoes, and the thermal conductivities of foods are very well tabulated because they're a huge issue in the food industry. So we've got that thermal conductivity, and the question is, what heat rate is necessary to maintain the top surface under these specified conditions? So in our last example, we started with the differential form of Fourier's law, and we saw that it very quickly collapsed into this sort of incremental form of Fourier's law because it's a very simple linear geometry. So we'll just start with this expression because, again, this is unidirectional heat transfer in a very simple situation. And we want to calculate that heat flow. That's what the question's asking for, heat rate. And that's going to be in units of watts or joules per second rather than Q, which is in units of watts per meter squared. So to calculate that, we just plug in the pieces of this equation. So K, we have a value for that. The area is pi times our diameter squared over 4. Delta T, it's pretty clearly 10 degrees, and in this case, 10 degrees Kelvin is the same as a delta 10 degrees centigrade because it's a delta. Is it positive or negative? Well, since heat is flowing in this direction, it basically means the final minus the initial on our coordinate axis is 60 minus 70. So it's a negative 10 degrees that we plug into here. And our delta x is a positive 0.005 meters because, again, the delta is final minus initial, and so this point is 0.005 and this point is 0, so final minus initial is a positive value in this case. And when we do that, we get that the heat rate is positive valued, and it's, if I compute this, 2.17 watts. And that's for a single slab. Okay, so that's the answer to part 1. Part 2 asks us, given a tray holds 30 slabs, how long does it cost to keep it running for 40 hours in the week? And I've given you here the value for the electrical cost based in Auckland, New Zealand, which is where I was living when I wrote this question. So this is kind of just a dimensional analysis question. The cost is going to be the energy per slab. So that's 2.17 watts per slab times the number of slabs. We've got 30 slabs. That gives us our energy flow in watts. We need to change that to kilowatts. So that's 1,000 watts per kilowatt, or 0.001 kilowatts per watt. That's our answer in kilowatts. Now we need units of energy, so we multiply by time, 40 hours. That's kilowatt hours. And finally, we multiply by the price per hour, which is 0.27 New Zealand dollars per hour. And that gives us a total cost of 70 cents. Not very expensive to run this potato tray all week long. The final part of the question is a little bit evaluative. It asks us to analyze why the answer we've computed is probably not correct, not explicitly correct. And I mean, there's a couple of reasons. One is that, like, if this is our tray and you're packing potato rounds onto it, even if they're all the same size, they're not covering the entire surface area of the tray. And so heat is coming off of the tray itself. We've said that they were adiabatic here, and obviously this is not an adiabatic situation. Heat is being lost into the ambient mainly via convection, which we'll learn about more in chapter 7, but just know that there is such a thing as convection. There could even be radiative heat losses, though those only really become significant at high temperatures, generally. Also, we haven't considered transients, by which I mean when you start up the heater in the morning and when you turn it off in the evening, the heat flow is changing as it gets up to its equilibrium temperature. And so that's going to be, an integration of energy over that time period rather than a constant value. So for all of these reasons, the value that we've calculated is not going to be the value that someone actually pays. But it's probably relatively close. And as an engineer, that's all we're aiming for. I mean, if you get the right order of magnitude estimate, you're usually doing a pretty good job. So thank you. See you for the next example.